Tonight, we're going to talk about one of humanity's most audacious achievements. Two machines, launched in 1977, designed to last 5 years, are still calling home nearly 50 years later from the edge of interstellar space. They've traveled farther than any human-made object in history. They've seen things no one had ever seen before. And what they found changed everything we thought we knew about our solar system and our place in the universe. By the end of tonight, you're going to understand why these two spacecraft, Voyager 1 and Voyager 2, are among the most important scientific instruments ever built. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. September 5th, 1977, Cape Canaveral, Florida. A Titan Centaur rocket sits on the launch pad, carrying a spacecraft that weighs about as much as a small car. Voyager 1. 2 weeks earlier, on August 20th, its twin, Voyager 2, had already lifted off on a slower trajectory. Both spacecraft were built for one mission: visit Jupiter and Saturn, take pictures, gather data, and then drift into the void. 5 years, maybe. That was the plan. The engineering teams at NASA's Jet Propulsion Laboratory in Pasadena had designed these spacecraft with remarkable care. Every component was chosen for reliability. Every system had backups. They knew these machines would face extremes no spacecraft had ever encountered. The intense radiation around Jupiter that could fry electronics. The freezing cold of the outer solar system, where temperatures drop to -328 degrees Fahrenheit or -200 degrees Celsius. The vast distances where sunlight becomes too weak to power solar panels. So Voyager was built differently. It carried 3 radioisotope thermoelectric generators, RTGs, devices that convert heat from decaying plutonium-238 into electricity. No solar panels, no dependence on sunlight, just steady, reliable power from radioactive decay that would last for decades. The spacecraft carried 11 scientific instruments: cameras to photograph the planets and their moons, spectrometers to analyze the composition of atmospheres, magnetometers to measure magnetic fields, plasma detectors to study the solar wind, cosmic ray instruments to detect high-energy particles from beyond the solar system. Each instrument was designed to answer specific questions about the outer planets. But here's what made Voyager truly special: the timing. In the late 1970s, the outer planets were aligning in a configuration that happens only once every 175 years. Jupiter, Saturn, Uranus, and Neptune would be positioned such that a spacecraft could visit all 4 by using gravity assists. Swing past Jupiter, and Jupiter's gravity would accelerate the spacecraft and bend its path towards Saturn. Swing past Saturn, same thing. Each planet acting as a gravitational slingshot, adding speed and changing direction without burning any fuel. This was called the Grand Tour, a single mission to all 4 gas giants. But NASA didn't have funding for such an ambitious mission. So Voyager was officially designed just for Jupiter and Saturn. The Grand Tour would happen only if the spacecraft survived that long and if mission controllers could convince NASA to extend the mission. Voyager 2 launched first because it was taking a slower route. Voyager 1 launched 2 weeks later, but on a faster trajectory that would overtake its twin within months. The journey to Jupiter would take about 18 months. During that time, the spacecraft cruised through the inner solar system, testing its instruments, calibrating its cameras, and transmitting data back to Earth. Think about what 18 months means for a spacecraft traveling to Jupiter. The distance from Earth to Jupiter varies because both planets are orbiting the Sun. At its closest approach, Jupiter is about 390 million miles from Earth. At its farthest, about 600 million miles. Voyager had to be launched at precisely the right time to intercept Jupiter at the optimal point in its orbit. The launch window was narrow. Miss it by a few weeks, and you'd have to wait years for the next opportunity. The trajectory was calculated years in advance. Engineers had to account for the gravitational pull of the Sun, the motion of Earth, the motion of Jupiter, the thrust from the rocket, every tiny force that would affect the spacecraft's path. One small error in the calculations, one miscalibration of the rocket's thrust, one unexpected perturbation, and Voyager could miss Jupiter by millions of miles. The precision required was extraordinary. The Deep Space Network, a collection of massive radio antennas in California, Spain, and Australia, tracked both spacecraft continuously. These antennas are enormous. The main dish at Goldstone in California's Mojave Desert is 230 feet in diameter. That's as wide as a football field is long. The antenna can detect signals from Voyager that are weaker than the energy from a snowflake hitting the ground. Think about that. A spacecraft billions of miles away, transmitting with a radio transmitter that uses less power than a refrigerator light bulb, and we can hear it. Every command sent from Earth took time to reach Voyager. At Jupiter's distance, radio signals traveling at the speed of light took about 45 minutes one way. Send a command. Wait 45 minutes for it to arrive. Voyager processes the command, sends a response, and you wait another 45 minutes for the response to come back. 90 minutes, round trip, for any communication. By the time Voyager reached Saturn, the round-trip light time was over 2 hours. At Uranus, over 5 hours. At Neptune, over 8 hours. By the time Voyager reached interstellar space, we're talking about 45 hours for a round-trip communication. Send a command today, hear back almost 2 days later. This meant the spacecraft had to be autonomous. It couldn't wait for instructions from Earth to react to problems. If something went wrong, if an instrument failed, if the spacecraft's orientation drifted, if a computer glitched, Voyager had to diagnose the issue and fix it on its own. The engineers built in layers of redundancy, 2 computers, so if one failed, the other could take over. Backup systems for critical components. Fault protection algorithms that would automatically safe the spacecraft if certain errors were detected. The spacecraft could reboot itself, switch to backup systems, and continue the mission without human intervention. It had to. By the time mission controllers on Earth realized there was a problem, hours would have passed. The situation could have changed completely. The spacecraft could have tumbled out of control or shut down entirely. So Voyager was designed to handle problems autonomously, to keep itself alive and operating until engineers on Earth could diagnose the issue and send corrective commands. Voyager 1 reached Jupiter on March 5, 1979. The images started arriving weeks earlier. Even from millions of miles away, Voyager's cameras could see Jupiter in detail that exceeded the best telescopes on Earth. The Great Red Spot, a storm larger than Earth that had been raging for centuries, appeared in stunning clarity. Bands of clouds stretched across the planet, swirling in complex patterns driven by Jupiter's rapid rotation. The planet spins once every 10 hours, creating powerful jet streams in its atmosphere. But the real surprises came when Voyager turned its cameras to Jupiter's moons. Io, the innermost of the 4 large moons discovered by Galileo in 1610, looked like nothing anyone expected. Its surface was covered in yellows, oranges, and reds, colors you'd never expect on a moon. Most moons in the solar system are gray or brownish, covered in ancient craters from billions of years of meteorite impacts. But Io looked different. Vibrant colors, splotches of sulfur and sulfur compounds, painting the surface in yellows and oranges. And here's what was truly strange. No impact craters. On a moon that should have been pummeled by meteorites for billions of years, there were no craters. Or rather, there were a few, but far fewer than there should have been. The surface looked young, fresh, like something was constantly renewing it, covering up the old craters. Linda Morabito, a navigation engineer working on the Voyager imaging team, was processing images to track Io's position when she noticed something odd. She wasn't looking for volcanoes. She was doing routine navigation work, measuring the positions of stars and satellites to help calculate Voyager's exact trajectory. Standard procedure. But in one image, she saw something that shouldn't be there. A bright plume extending from Io's limb, an arc of material shooting up from the moon's edge. At first, she thought it might be an artifact, a glitch in the image processing, a cosmic ray hitting the camera's detector. These things happen in space photography. But she checked other images. The plume was real. She enhanced the image, adjusted the contrast, brought out the details. It was a volcano, an active volcano erupting on Io. Material blasting hundreds of miles above the surface. This was March 1979. The first time in human history anyone had witnessed active volcanism beyond Earth. The announcement sent shockwaves through the scientific community. Volcanism on a moon of Jupiter? No one expected this. Io is tiny compared to Earth, about the size of our moon. Small bodies cool down quickly. They lose their internal heat within 1 billion years or so after formation. Earth is still geologically active because it's large enough to retain heat from its formation and from radioactive decay in its interior. But Io should have been cold and dead billions of years ago. Yet, here it was, erupting. Not just one volcano, either. As Voyager 1 continued its flyby and took more images, more volcanoes appeared. By the time the encounter was over, scientists had identified 9 active volcanoes, 9 separate eruption sites scattered across Io's surface. 4 months later, when Voyager 2 arrived at Jupiter in July 1979, it turned its cameras to Io. 8 of those 9 volcanoes were still erupting. The same volcanoes, still active, 4 months later. One had apparently shut down. But a new one had started up. The level of volcanic activity was astonishing. Io wasn't just occasionally volcanic. It was constantly erupting. Multiple volcanoes, active at any given time. The eruption plumes reached heights of over 200 miles. Some of the plumes were so large they could be seen from the edge of Io's disk when the moon was backlit by Jupiter. Material was being blasted off the surface at speeds of over 0.5 mile per second. Faster than a bullet. The eruptions were launching sulfur and sulfur dioxide into space. Some of this material escaped Io entirely and formed a torus, a donut-shaped cloud of particles, around Jupiter in Io's orbital path. Voyager's instruments detected this sulfur torus. a glowing ring of ionized sulfur atoms circling Jupiter at Io's distance. The reason for this intense volcanic activity became clear when scientists analyzed Io's orbit. Io is locked in a gravitational tug-of-war between Jupiter and the other large moons, Europa and Ganymede. Their orbits are in resonance. For every one orbit Io makes around Jupiter, Europa makes exactly 2 orbits, and Ganymede makes exactly 4. This resonance locks the moons together gravitationally. Europa and Ganymede pull on Io, preventing its orbit from becoming perfectly circular. The orbit remains slightly elliptical. And because the orbit is elliptical, Io's distance from Jupiter varies as it orbits. When Io is closer to Jupiter, Jupiter's gravity pulls harder. When it's farther away, the pull is weaker. This varying gravitational pull stretches and squeezes Io continuously. The solid surface of the moon flexes up and down by about 300 feet. Imagine the ground beneath your feet rising and falling by the height of a 30-story building, twice a day, every day, for billions of years. The friction from this constant flexing generates enormous heat inside Io. Enough heat to melt rock. The interior of Io is probably partially molten, a global magma ocean beneath a thin, solid crust. And that magma finds its way to the surface through volcanoes. Io is the most volcanically active body in the entire solar system. More volcanic activity than Earth, despite being a quarter of Earth's diameter. The surface is constantly being resurfaced by lava flows and volcanic deposits. That's why there are so few impact craters. Any crater that forms gets buried under fresh volcanic material within a few million years. The entire surface of Io is replaced every million years or so. In geological terms, that's incredibly fast. It means the Io we see today looks completely different from the Io that existed a million years ago. And a million years from now, it will look different again. Europa, the next moon out, was completely different. Its surface was smooth, covered in ice, crisscrossed with long cracks and lines. The smoothest object in the solar system. When scientists say smooth, they mean it. Europa has almost no mountains, no deep valleys, no significant elevation changes. The whole surface is remarkably flat. Very few craters, suggesting the surface was young, constantly renewed. But renewed by what? Not volcanoes, like Io. Europa showed no signs of volcanic activity. Instead, the surface looked like it was made of water ice. And the cracks, the long linear features crisscrossing the surface, looked like fractures in ice. Scientists began to suspect what those cracks meant. Europa's icy crust might be floating on a vast ocean of liquid water beneath. Here's the evidence they pieced together. First, Europa's density suggests it has a large water component. The moon is less dense than rock, but denser than pure ice. This is consistent with a rocky core surrounded by a thick layer of water and ice. Second, the lack of craters and the presence of those cracks indicate the surface is geologically young. Something is resurfacing Europa, covering up old craters. On Earth, we see similar crack patterns in sea ice. When ice floats on liquid water and gets pushed around by currents or tides, it fractures and refreezes in these characteristic patterns. Europa's surface looks like that. Third, the same tidal forces that heat Io might be heating Europa. Europa is also in an orbital resonance with Io and Ganymede. Its orbit is slightly elliptical, so it experiences tidal flexing as it orbits Jupiter. Not as extreme as Io's tidal heating, but enough to generate significant heat. Enough, potentially, to keep a subsurface ocean liquid. Fourth, Voyager's measurements of Europa's magnetic field were suggestive. The way Europa responds to Jupiter's rotating magnetic field is consistent with the presence of a conducting layer beneath the surface. Salty water conducts electricity. Pure ice doesn't. So, if there's a conducting layer beneath Europa's ice, it's probably liquid water with dissolved salts. Scientists calculated that Europa might have a global ocean beneath its ice crust. An ocean, perhaps 60 miles deep. The ice crust on top might be anywhere from a few miles to tens of miles thick. But beneath that ice, liquid water. And if the estimates are correct, Europa's ocean contains more water than all of Earth's oceans combined. Think about that. A moon smaller than our moon, orbiting Jupiter, might contain more liquid water than our entire planet. All of it beneath a frozen crust. An entire alien ocean we can't see directly. And where there's liquid water, especially liquid water that's been stable for billions of years, there's the possibility of life. On Earth, life exists almost everywhere there's liquid water. Deep in the oceans, near hydrothermal vents where no sunlight reaches. In underground caves filled with water. In frozen lakes beneath Antarctic ice sheets. Wherever water remains liquid, life finds a way. If Europa has a subsurface ocean, and if that ocean has existed for billions of years, and if there are energy sources, like hydrothermal vents on the ocean floor, then Europa could potentially harbor life. Not necessarily complex life. Probably microbial. Simple organisms adapted to the dark, cold conditions beneath the ice. But life, nonetheless. This possibility transformed how scientists think about habitable environments in the solar system. Before Voyager, the focus was on planets in the habitable zone, the region around a star where temperatures are right for liquid water to exist on a planet's surface. For our solar system, that's roughly the orbit of Earth. Mars is at the outer edge. Venus is at the inner edge, though it's too hot now due to its runaway greenhouse effect. But Europa is far outside the habitable zone. It's 5 times farther from the Sun than Earth. Sunlight at Jupiter is only 4% as intense as sunlight at Earth. The surface of Europa is frozen solid at temperatures around -256 degrees Fahrenheit or -160 degrees Celsius. By traditional habitable zone thinking, Europa should be dead. But if it has a subsurface ocean kept warm by tidal heating, then Europa is potentially habitable, despite being nowhere near the traditional habitable zone. This opened up the possibility that habitable environments might exist on many moons throughout the solar system and beyond. Anywhere a moon experiences tidal heating strong enough to maintain liquid water beneath its surface. Later missions would confirm much of what Voyager suggested. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, provided strong evidence for Europa's subsurface ocean. It detected changes in Europa's magnetic field consistent with an electrically conducting layer beneath the surface. It found more evidence of recent geological activity. And more recent analysis suggests Europa's ocean might be in direct contact with the rocky seafloor, which would allow for chemical interactions between water and rock. On Earth, those interactions at hydrothermal vents provide energy that supports entire ecosystems independent of sunlight. Europa might have the same thing, a potential ecosystem in a dark ocean beneath miles of ice. All because of what Voyager found in 1979. Ganymede, the largest moon in the solar system, bigger even than the planet Mercury, showed a complex surface of old dark terrain and younger bright terrain, grooved and ridged. Callisto, the outermost of the 4 large moons, was heavily cratered, the most cratered object in the solar system. Its surface, a record of billions of years of impacts. And then, Voyager found something no one had predicted. Jupiter has rings. Thin, faint rings made of dust and small particles, encircling the planet. Saturn's rings had been known since Galileo first saw them in 1610, though he didn't know what they were. But Jupiter's rings were invisible from Earth, too faint, too thin to see with telescopes. Voyager discovered them by chance when its cameras happened to look back at Jupiter with the sun behind it, illuminating the dust. This discovery forced scientists to rethink their theories about planetary rings. If Jupiter had rings, maybe all the gas giants did. After Jupiter, both Voyagers continued towards Saturn. The journey took about a year and a half. Voyager 1 arrived in November 1980. Voyager 2 followed 9 months later, in August 1981. Saturn is farther from the Sun than Jupiter, colder, less massive, but in many ways more spectacular. The rings. Saturn's rings had been observed for centuries, but no one fully understood what they were seeing. When Galileo first pointed his telescope at Saturn in 1610, he saw what looked like handles or ears on either side of the planet. His telescope wasn't powerful enough to resolve the rings properly. He thought Saturn might be 3 bodies close together. Over the following years, as Saturn's orientation changed in its orbit, the rings appeared to vanish, then reappear. Galileo was baffled. It wasn't until 1655 that Christian Huygens, using a better telescope, correctly identified them as a flat ring surrounding the planet, but not touching it. In 1675, Giovanni Cassini discovered that the rings weren't uniform. There was a gap, a division in the rings, now called the Cassini division in his honor. By the time Voyager arrived, astronomers knew the rings were made of ice and rock particles orbiting Saturn. They knew about the main divisions in the ring system, but they didn't know the details. How thick were the rings? How many individual particles made them up? What processes shaped their structure? Voyager revealed the answers. And the answers were stunning. What appeared through telescopes as a few distinct rings, labeled A, B, C, D, E, F, and G, from outer to inner, were actually thousands of ringlets. Narrow bands of ice and rock particles separated by gaps. The rings showed structure on every scale. Broad divisions, visible from Earth. Narrower gaps, visible only in close-up images. And even finer structure within each ringlet. Variations in brightness, in particle density, in orbital dynamics. The Cassini division, the large gap in the rings visible from Earth, wasn't empty. It contained its own faint ringlets. Dozens of them, each one a separate concentration of particles in a slightly different orbit. The rings showed features no one had predicted. Braided rings, where gravitational interactions with small moons created twisted, rope-like patterns. The F-ring, a narrow ring just outside the main ring system, appeared braided. 3 separate strands twisted around each other like a rope. This braiding was caused by 2 small moons, Prometheus and Pandora, orbiting on either side of the F ring. Their gravity shepherded the ring particles, keeping them confined to a narrow band, but also creating complex orbital resonances that made the ring particles weave in and out. Spokes, mysterious dark features that rotated with the rings. These spokes were radial features, extending outward from Saturn like spokes on a wheel. They rotated with the rings, but they didn't behave like solid objects. Ring particles at different distances from Saturn orbit at different speeds. Particles closer to Saturn move faster, particles farther out move slower. So any solid feature would get sheared apart quickly. But the spokes maintained their shape for hours as they rotated. Scientists eventually figured out that the spokes were caused by electromagnetic forces. Fine dust particles, smaller than the typical ring particles, could be levitated above the ring plane by electrical charges and magnetic forces. These levitated particles formed the spokes, which could move together without being sheared apart by differential rotation. The spokes appeared and disappeared in a matter of hours, a dynamic feature in what otherwise seemed like a static ring system. Density waves in the rings, ripples propagating through the ring system like waves on water. These were caused by gravitational resonances with Saturn's moons. When ring particles orbit at a specific distance from Saturn, such that they complete, say, exactly 2 orbits for every 1 orbit of a particular moon, they experience periodic gravitational tugs from that moon. These tugs add up over time and create waves that propagate through the ring system. The waves show up as spiral patterns of alternating high and low density. Voyager's images revealed dozens of these density waves at different locations in the rings, each one corresponding to a resonance with a particular moon. The rings were far thinner than anyone expected. In some places, the rings are only 30 feet thick. Think about that. Saturn's rings span over 175,000 miles from edge to edge. But they're only 30 feet thick in places. That's an aspect ratio of nearly 6 billion to 1. If you scaled the rings down to the size of a sheet of paper, they would be far thinner than paper. They would be about 100,000 times thinner than paper. The thinness of the rings tells us about their age and evolution. Collisions between ring particles tend to flatten the ring system over time. Particles with vertical motion eventually collide with other particles and settle into the same plane. The fact that the rings are so thin suggests they've had time to settle. They're probably not newly formed, but they're also probably not billions of years old. Ring particles are constantly being ground down by collisions and micrometeorite impacts. They're also being lost to Saturn's atmosphere through a process called ring rain. Charged particles from the rings spiral down magnetic field lines and fall into Saturn's upper atmosphere. If the rings were billions of years old, they should have been eroded away by now. Current estimates, based on Voyager's observations and later data from the Cassini mission, suggest Saturn's rings might be only a few 100 million years old. Young, in cosmic terms. Maybe formed when a moon or comet wandered too close to Saturn and was torn apart by tidal forces. The debris from that catastrophic breakup spread out into rings and has been evolving ever since. Voyager 2 flew so close to the rings that the mission team could hear them. Not literally hear, because sound doesn't travel through the vacuum of space. But Voyager's radio and plasma wave instrument detected impacts. Tiny dust grains from the rings bombarding the spacecraft created electrical signals as they hit and vaporized. The instrument recorded hundreds of impacts per second as Voyager passed through the ring plane. Each impact a microscopic grain of ring material, no bigger than a speck of dust. But traveling at miles per second relative to the spacecraft, these tiny grains packed enough energy to create detectable signals. The spacecraft survived unharmed. The impacts were too small to cause damage. But the data they provided was invaluable, giving scientists direct information about the size and distribution of the smallest ring particles. Both spacecraft studied Saturn's atmosphere. The planet is a gas giant, similar to Jupiter but less massive. Its atmosphere is mostly hydrogen and helium, with traces of methane, ammonia, and other compounds. Wind speeds exceeded 1,000 miles per hour near the equator. Jet streams, bands of fast-moving air circling the planet at different latitudes. Storms, though not as prominent or long-lived as Jupiter's Great Red Spot. One fascinating discovery was Saturn's hexagonal storm at its North Pole. This feature wasn't noticed until later analysis of Voyager images, but it's remarkable. A hexagon-shaped jet stream at the North Pole, about 20,000 miles across. 6 relatively straight sides, forming a nearly perfect hexagon. No one had ever seen anything like it on any other planet. The hexagon is a standing wave in the jet stream, maintained by the specific combination of wind speeds and Coriolis forces at that latitude. Laboratory experiments have recreated similar hexagonal patterns in rotating fluids, but seeing it on a planetary scale is extraordinary. The hexagon has persisted for decades. It's still there today, still visible in images from later missions, a permanent feature of Saturn's atmosphere. Voyager measured Saturn's magnetic field and found it was nearly aligned with the planet's rotation axis, unlike Jupiter's tilted field. The field was weaker than Jupiter's, but still substantial, strong enough to trap charged particles and create radiation belts around the planet, though not as intense as Jupiter's radiation. But the most important target at Saturn was Titan. Titan is Saturn's largest moon and the second largest moon in the solar system after Ganymede. It's bigger than the planet Mercury, and it's the only moon with a thick atmosphere. From Earth, Titan appears as a featureless orange ball. Its atmosphere is so thick and hazy that visible light can't penetrate to the surface. Astronomers could see the atmosphere, a layer of haze surrounding the moon, but they couldn't see through it to the surface below. Spectroscopic observations from Earth showed the atmosphere contained methane and other organic compounds, but the details were unclear. How thick was the atmosphere? What was its composition? What was the surface like beneath the haze? Was there liquid on the surface? Titan was a mystery. Scientists knew it had an atmosphere, which made it unique among moons. Our moon doesn't have an atmosphere. Most moons don't. They're too small, their gravity too weak to hold onto gases. But Titan is large and cold. At Saturn's distance from the Sun, temperatures are low enough that gases don't escape easily. Titan could hold onto an atmosphere. Voyager 1 was targeted to fly close to Titan. This was a critical decision. Flying close to Titan meant Voyager 1's trajectory would be bent by Titan's gravity. The spacecraft would be deflected out of the plane of the solar system. It would head northward, up and away from the ecliptic. It would never encounter another planet. The grand tour would end at Saturn for Voyager 1. But the scientific returns from studying Titan were considered worth it. Titan was the highest priority target at Saturn, nearly as important as Saturn itself. The spacecraft passed within 4,000 miles of Titan's surface, closer than Voyager had flown to any moon except Io. What it found was remarkable. Titan's atmosphere is denser than Earth's. Surface pressure about 1.5 times Earth's sea level pressure. If you stood on Titan's surface, the atmospheric pressure would feel similar to being about 15 feet underwater on Earth. Not crushingly high, but definitely noticeable. The atmosphere is 98% nitrogen, almost pure nitrogen, just like Earth's atmosphere, which is 78% nitrogen and 21% oxygen. Titan's atmosphere is even more nitrogen-dominated than Earth's. The remaining 2% is mostly methane, with traces of hydrogen, ethane, and other hydrocarbons. The methane was particularly interesting. Sunlight breaks down methane in the atmosphere. Ultraviolet light from the sun splits methane molecules into carbon and hydrogen. The hydrogen, being light, escapes to space. The carbon combines with other atoms to form more complex organic molecules. This process should deplete Titan's atmospheric methane within about 10 million years. But Titan still has methane in its atmosphere. Lots of it. So something must be replenishing it. Either there's a source of methane on the surface, or it's being produced by geological processes, or possibly even biological processes, though biology seemed unlikely given the extreme cold. Titan's surface temperature is negative 290 degrees Fahrenheit, or negative 179 degrees Celsius. Cold enough that water ice is as hard as granite. At that temperature, methane can exist as a liquid. In fact, methane on Titan behaves the way water does on Earth. It evaporates from the surface, forms clouds in the atmosphere, condenses and falls as rain, flows in rivers, collects in lakes and seas. There's a methane cycle on Titan, analogous to Earth's water cycle. Voyager's instruments detected complex organic compounds in Titan's atmosphere. Hydrocarbons, molecules made of carbon and hydrogen. Ethane, propane, acetylene, ethylene. And larger molecules called tholins, complex organic compounds that form when simpler molecules are exposed to ultraviolet light or electrical discharges. Tholins are responsible for the orange haze that hides Titan's surface. They form high in the atmosphere and slowly settle down, creating a thick smog layer. Scientists began to think of Titan as a frozen version of early Earth. Earth's atmosphere 4 billion years ago, before life produced oxygen, was probably rich in nitrogen and methane. Organic chemistry was happening in the atmosphere, creating complex molecules. Some scientists think this atmospheric chemistry might have contributed to the origin of life on Earth, providing raw materials that eventually led to the first living organisms. Titan might have similar chemistry happening today, not leading to life, because it's too cold for the kinds of biochemical reactions we see in Earth's life. But still, organic chemistry on a planetary scale, creating complex molecules, raining them down to the surface, building up deposits of organic material. Titan's surface might be covered in layers of organic compounds. Frozen methane lakes, seas of liquid ethane and methane, riverbeds carved by flowing methane, dunes made of frozen organic particles. All of this was speculation based on Voyager's data. The spacecraft couldn't see through the haze to image the surface. But the atmospheric data was enough to paint a picture of a world unlike anywhere else in the solar system. A world with weather, with seasons, with a liquid cycle, with complex organic chemistry. All happening at temperatures cold enough to freeze carbon dioxide solid. Later, missions would confirm much of what Voyager suggested. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, carried a radar instrument that could see through Titan's haze. It mapped the surface and found exactly what Voyager's data suggested: lakes and seas of liquid methane and ethane at the poles, river channels carved by liquid methane, dunes of frozen organic material at the equator, mountains made of water ice, a world with an active hydrological cycle, just running on methane instead of water. And in 2005, the Huygens probe, carried to Saturn by Cassini, descended through Titan's atmosphere and landed on the surface. It sent back images and data from the surface of Titan. The first time a spacecraft had ever landed on a moon in the outer solar system. All of that was built on the foundation of what Voyager discovered. After Saturn, Voyager 1's mission to the planets was complete. Its trajectory sent it above the plane of the solar system, heading outward and northward. It would never encounter another planet. But Voyager 2 had a choice. Mission planners had designed its trajectory at Saturn to preserve the option of continuing to Uranus. Saturn's gravity could bend Voyager 2's path toward Uranus if NASA approved the extended mission. There was debate. The spacecraft had already exceeded its design life. Could it survive another 5 years to reach Uranus? Were the scientific returns worth the cost of continuing to operate the mission? NASA approved. Voyager 2 would continue to Uranus. The journey took 4.5 years. Voyager 2 arrived at Uranus in January 1986. Uranus is strange. It's tipped on its side. Most planets spin roughly upright relative to the plane of their orbit around the Sun. Earth is tilted 23.5 degrees, which gives us seasons. But Uranus is tilted 98 degrees. It's essentially rolling around the Sun on its side. This means Uranus has the most extreme seasons in the solar system. Each pole spends 42 years in continuous sunlight, then 42 years in continuous darkness. When Voyager 2 arrived, Uranus's south pole was pointed almost directly at the Sun. The planet appeared as a featureless blue-green ball. Its atmosphere is mostly hydrogen and helium, like Jupiter and Saturn, but with more methane. Methane absorbs red light and reflects blue-green light, giving Uranus its color. Voyager 2 found that Uranus's atmosphere was calm compared to Jupiter and Saturn. Few clouds, weak winds, not much activity. This might have been because of the timing. With the pole pointed at the Sun, there wasn't much temperature difference between the illuminated and dark sides of the planet to drive weather. The magnetic field was a surprise. Uranus's magnetic field is tilted 60 degrees from its rotation axis and offset from the planet's center. This is very unusual. Earth's magnetic field is roughly aligned with its rotation axis. Jupiter and Saturn's fields are also mostly aligned, but Uranus's field is wildly tilted. Scientists still don't fully understand why. Voyager 2 discovered 10 new moons around Uranus. Previously, 5 moons were known. Voyager brought the total to 15. The moons showed varied surfaces. Miranda, the smallest of the 5 original moons, was bizarre. Its surface looked like it had been taken apart and reassembled wrong. Huge cliffs, canyons deeper than the Grand Canyon, regions of different terrain, all jumbled together. One theory is that Miranda was shattered by a massive impact early in its history, and the pieces reassembled under their own gravity, but didn't quite fit back together the way they were before. And Uranus has rings. 9 narrow rings, discovered from Earth in 1977, when Uranus passed in front of a star and the rings blocked the starlight. Voyager 2 confirmed the rings and discovered 2 more. Uranus's rings are dark, made of particles that reflect very little light. They're very different from Saturn's bright icy rings. After Uranus, Voyager 2 had one more target: Neptune. 3.5 more years of travel. Voyager 2 reached Neptune in August 1989, 12 years after launch. Neptune is the farthest planet from the Sun, about 30 times Earth's distance from the Sun. It receives 900 times less sunlight than Earth. It's cold, dark, and it shouldn't have much going on. But Neptune surprised everyone. It had the most active atmosphere of any of the outer planets. Huge storms. The Great Dark Spot, a storm system the size of Earth, similar to Jupiter's Great Red Spot. Winds blowing at over 1,200 miles per hour, the fastest winds measured on any planet in the solar system. How could a planet so far from the Sun, receiving so little energy, have such powerful weather? Scientists realized Neptune must have an internal heat source. The planet radiates more than twice as much heat as it receives from the Sun. This internal heat drives the atmospheric circulation and creates the powerful storms. Neptune's blue color is more vivid than Uranus's blue-green, also caused by methane in the atmosphere. But Neptune's deeper blue suggests additional compounds are present, possibly organic molecules formed in the upper atmosphere. Like Uranus, Neptune's magnetic field was tilted and offset, 47 degrees from the rotation axis. This suggested that the odd magnetic fields of both Uranus and Neptune might be caused by something about how these planets generate their magnetic fields. Perhaps the fields are generated in a shell of conducting material deep inside the planets, rather than in the core, like Earth's field. Voyager 2 discovered 6 new moons around Neptune, bringing the total to 8. The largest moon, Triton, was Voyager 2's final planetary target. Voyager flew within 5,000 miles of Triton's surface. Triton is unusual because it orbits Neptune backward. Retrograde orbit. Every other large moon in the solar system orbits in the same direction its planet rotates. Triton orbits the opposite way. This strongly suggests Triton didn't form around Neptune. It was captured. Triton is probably a Kuiper belt object, similar to Pluto, that wandered too close to Neptune billions of years ago and was captured by the planet's gravity. Triton's surface is frozen nitrogen. The temperature is -391 degrees Fahrenheit, or -235 degrees Celsius, one of the coldest surfaces in the solar system. But Voyager found something astonishing. Triton has active geysers, plumes of nitrogen gas erupting from the surface, carrying dark material high into the thin atmosphere. Geysers on a moon colder than any freezer on Earth. The mechanism is thought to be seasonal heating. Even though Triton is incredibly cold, when the sun shines on transparent nitrogen ice, it can create a greenhouse effect beneath the surface. The ice traps heat, pressure builds up, and eventually the nitrogen erupts through weak spots in the crust. Neptune also has rings. 5 narrow rings, faint and dark, like Uranus's rings. Voyager 2's encounter with Neptune was the end of the Grand Tour. 4 planets, 48 moons, 4 ring systems. 12 years of exploration. Over the course of those 12 years, the 2 Voyager spacecraft had fundamentally changed our understanding of the outer solar system. They had revealed worlds of incredible complexity and diversity. Volcanic moons, subsurface oceans, thick atmospheres, rings around every gas giant, magnetic fields, active geology on moons that should have been dead. Every expectation had been overturned. Every planet and moon was unique. But Voyager's mission wasn't finished. After Neptune, both spacecraft were heading out of the solar system. They were still functioning, still sending data. Power levels were good. Most instruments were still working. And scientists realized they could use Voyager to study something no spacecraft had ever studied before: the edge of the solar system. The boundary where the sun's influence ends and interstellar space begins. This boundary is called the heliopause. To understand what the heliopause is, you need to understand the solar wind. The sun doesn't just emit light and heat. It also emits a constant stream of charged particles, protons and electrons, flowing outward in all directions. This is the solar wind. The sun's corona, its outermost atmosphere, is so hot, over 1,800,000 degrees Fahrenheit, or over 1,000,000 degrees Celsius, that particles have enough energy to escape the sun's gravity. They stream outward at speeds of about 300 to 500 miles per second. The solar wind is tenuous. Only a few particles per cubic centimeter near Earth. Much more tenuous than the best vacuum we can create in a laboratory. But it's moving fast, and there's a lot of it. The sun loses about 1 million tons of material per second through the solar wind. Over the sun's lifetime of 4.5 billion years, it's lost a tiny fraction of its total mass this way. Less than 1 part in 10,000. But still, a continuous stream of particles flowing outward. The solar wind carries the sun's magnetic field with it. This creates a magnetic bubble around the sun, called the heliosphere. The heliosphere extends far beyond the planets. It's shaped like a bubble being blown through the interstellar medium. Imagine the sun moving through space at about 43,000 miles per hour relative to the surrounding interstellar clouds. That's fast by everyday standards, but slow compared to the solar wind's speed. The front of the heliosphere, in the direction the sun is moving, is compressed, like the bow wave of a ship moving through water. The back is stretched out into a long tail, called the heliotail, that extends for billions of miles behind the sun. As the solar wind flows outward, it eventually reaches a point where the pressure from interstellar space equals the pressure from the solar wind. Before that point, the solar wind is moving faster than the speed of sound in the solar wind plasma. Supersonic flow. At this boundary, the solar wind suddenly slows down to subsonic speeds. This is called the termination shock. It's analogous to a shock wave in front of a supersonic aircraft. The shock compresses and heats the solar wind. The particles slow down dramatically. The temperature increases. The magnetic field becomes stronger and more turbulent. Beyond the termination shock is a region called the heliosheath. In this region, the solar wind has slowed down and become turbulent, but it's still flowing outward. It's mixing with particles from the interstellar medium that are starting to penetrate the heliosphere. The magnetic field is tangled and variable. It's a transition zone between the solar-dominated inner heliosphere and the galactic-dominated interstellar medium. And finally, at the outermost edge, there's the heliopause, the boundary where the solar wind stops completely, where the pressure from the solar wind exactly balances the pressure from the interstellar medium. Beyond the heliopause is interstellar space, the space between stars, no longer dominated by the sun, but by the galaxy. Filled with the interstellar medium, a diffuse gas of mostly hydrogen and helium left over from the Big Bang, enriched with heavier elements from generations of stars that have lived and died. The interstellar medium also contains cosmic rays, high-energy particles from outside the solar system. Most of them are protons, hydrogen nuclei, traveling at nearly the speed of light. They're accelerated by supernova explosions, by the shock waves from dying stars, by rotating magnetic fields around neutron stars and black holes. These particles carry enormous energy. A single cosmic ray proton can have as much kinetic energy as a baseball thrown at 60 miles per hour, all concentrated in a single atomic nucleus. When cosmic rays hit Earth's atmosphere, they create showers of secondary particles that cascade down through the atmosphere. We can detect these showers with instruments on the ground. Some cosmic rays are so energetic they can penetrate deep underground through solid rock. We build detectors in mines and under mountains to study them. The sun's magnetic field partially shields the inner solar system from cosmic rays. The heliosphere acts as a barrier, deflecting and scattering cosmic rays. Some still get through, especially the most energetic ones, but the intensity of cosmic rays near Earth is much lower than the intensity in interstellar space. No one knew exactly where the heliopause was before Voyager. Theoretical models predicted it should be somewhere between 80 and 120 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So we're talking about distances of 7 billion to 11 billion miles, far beyond the orbits of all the planets. Neptune, the outermost planet, orbits at about 30 astronomical units. The heliopause is 3 to 4 times farther out than Neptune. Voyager 1 crossed the termination shock in December 2004. The spacecraft was 94 astronomical units from the Sun, about 8.5 billion miles. The event was dramatic from a scientific perspective, though it took weeks of analysis to confirm what had happened. Voyager detected a sudden change in the solar wind. The speed dropped from about 250 miles per second to near zero. Almost overnight, the solar wind went from supersonic to essentially stagnant. The temperature increased dramatically, from about 40,000 Kelvin to over 300,000 Kelvin. The magnetic field strength increased and became highly variable. All signs that Voyager had crossed a shock, the termination shock. The boundary where the solar wind slams into the back pressure from the interstellar medium and suddenly slows down. For the next 8 years, Voyager 1 traveled through the heliosheath. During this time, scientists watched the spacecraft's instruments carefully. They were looking for signs that Voyager was approaching the heliopause. One key indicator was cosmic rays. Voyager carried instruments to detect cosmic rays, specifically the cosmic ray subsystem and the low-energy charged particle instrument. These instruments could measure the intensity and energy spectrum of incoming cosmic ray particles. In the heliosheath, cosmic ray intensity was higher than it had been inside the termination shock, but it was still being modulated by the Sun's activity. During solar maximum, when the Sun is most active and the solar wind is strongest, cosmic ray intensity decreases. The stronger solar wind and magnetic field push cosmic rays back more effectively. During solar minimum, when the Sun is quieter, cosmic ray intensity increases. More cosmic rays can penetrate closer to the inner solar system. Voyager was seeing these variations. The cosmic ray intensity went up and down in an 11-year cycle, matching the Sun's activity cycle. But scientists predicted that beyond the heliopause, this solar modulation would stop. The cosmic ray intensity would be constant, unaffected by solar activity, determined purely by galactic processes, not solar processes. In the years leading up to 2012, Voyager 1's cosmic ray detectors started seeing unusual behavior. Sudden jumps in cosmic ray intensity that would last for days or weeks, then drop back down. Scientists interpreted these as transient events. The heliopause wasn't a perfectly stationary boundary. It moved back and forth slightly, buffeted by changes in the solar wind pressure and interstellar wind pressure. Think of it like waves on a beach. The average position of the waterline is relatively stable, but individual waves push the water farther up the beach, then recede. The heliopause was similar. On average, it was at a certain distance from the Sun, but variations in solar wind pressure caused by solar storms and the solar activity cycle could push the heliopause outward, and variations in interstellar pressure could push it inward. Voyager was sampling these movements. When the heliopause moved inward past Voyager's position, the spacecraft briefly entered interstellar space. Cosmic rays increased, solar particles decreased. Then the heliopause moved back outward, and Voyager was in the heliosheath again. Cosmic rays dropped, solar particles returned. On May 8, 2012, Voyager saw a sudden 5% increase in cosmic ray intensity. It lasted for a few weeks, then dropped. On July 28th, another increase. Bigger this time, about 9%. Again, it lasted a few weeks and dropped. Scientists realized the heliopause was oscillating, moving back and forth across Voyager's position. The spacecraft was right at the boundary. Then, on August 25, 2012, Voyager 1 detected a sudden, dramatic change. Cosmic ray intensity jumped by about 25%. A huge increase. At the same time, the intensity of low-energy particles from the Sun, particles called anomalous cosmic rays that are accelerated in the heliosheath, dropped to nearly zero. These particles, effectively, disappeared. And unlike the previous events, this change didn't reverse. Days passed, then weeks, then months. The cosmic ray intensity stayed high. The solar particles stayed at zero. The spacecraft had crossed something. But what? The magnetic field was still pointing in the same direction it had been pointing in the heliosheath. Some theoretical models predicted that beyond the heliopause, in interstellar space, the magnetic field should change direction, point in a different direction than the solar magnetic field. But Voyager's magnetometer showed no change in direction. The field strength had increased, and the field was more turbulent, but the direction hadn't changed. This led to debate. Had Voyager crossed the heliopause, or had it crossed some other boundary? Maybe it had entered a new region within the heliosheath, a region where cosmic rays could flow more freely, but it was still technically within the Sun's domain. The debate lasted for months. Scientists analyzed the data from all of Voyager's working instruments. They compared the observations to theoretical models. They looked for additional evidence. One key piece of evidence came from Voyager's plasma wave instrument. This instrument detects oscillations in the plasma, the ionized gas, around the spacecraft. In April 2013, the instrument detected a sudden increase in plasma wave activity. The waves were being generated by an interaction between the solar wind and interstellar plasma. A burst of solar wind pressure had pushed outward and was now interacting with the interstellar medium beyond the heliopause. The interaction created waves that propagated back to Voyager's position. By analyzing these waves, scientists could measure the density of the plasma around Voyager. In the heliosheath, the plasma density was typically around 0.002 particles per cubic centimeter. Very low. But the waves indicated a plasma density of about 0.08 particles per cubic centimeter. 40 times denser. This was consistent with the expected density of the interstellar plasma. It took scientists several months to analyze this data and reach a conclusion. But by September 2013, the consensus was clear. Voyager 1 had crossed the heliopause. It was in interstellar space. NASA announced the finding at a press conference. Voyager 1, a spacecraft launched in 1977, designed to last 5 years, had become the first human-made object to leave the solar system and enter the space between the stars. At the time, Voyager 1 was about 11.25 billion miles from the Sun, about 121 astronomical units. Light from the Sun took about 16 hours and 40 minutes to reach that distance. Radio signals from Voyager, also traveling at the speed of light, took the same amount of time to reach Earth. Send a command to Voyager. Wait 16 hours and 40 minutes for it to arrive. Voyager processes the command and sends a response. Wait another 16 hours and 40 minutes for the response to come back. 33 hours and 20 minutes, round trip. More than a day and a half for a single exchange of information. Voyager 2 crossed the heliopause 6 years later, on November 5, 2018. At 119 astronomical units from the Sun, about 11 billion miles. Slightly closer than where Voyager 1 crossed. The heliopause isn't a sphere. It's shaped by the interaction between the solar wind and the interstellar wind. It's compressed in the direction the Sun is moving through space and stretched out behind. Voyager 1 crossed in a different direction than Voyager 2, so it crossed at a slightly different distance. For Voyager 2, the crossing was less ambiguous. Unlike Voyager 1, Voyager 2's plasma science instrument was still working. This instrument directly measures the solar wind. It can detect protons and electrons from the Sun and measure their speed, density, and temperature. On Voyager 1, this instrument had failed decades earlier. So scientists had to use indirect methods to infer what was happening with the solar wind. But on Voyager 2, they had direct measurements. And on November 5, 2018, the plasma science instrument saw the solar wind disappear. One day, it was there, flowing past the spacecraft at about 100 miles per second. The next day, it was gone. Completely gone. The instrument was no longer detecting any solar wind particles at all. At the same time, cosmic rays increased. low-energy particles from the heliosheath disappeared, and the plasma density jumped, just as it had for Voyager 1. Every instrument on Voyager 2 confirmed what was happening. The spacecraft had crossed the heliopause and entered interstellar space. And like Voyager 1, the magnetic field didn't change direction. This was puzzling. If both spacecraft saw the same thing, it probably wasn't a fluke or an instrument error. It was telling us something real about the structure of the heliopause and the interstellar magnetic field. The current understanding is that the interstellar magnetic field happens to be oriented in a similar direction to the solar magnetic field in this region of space. So, when the spacecraft crossed from the heliosphere to the interstellar medium, they didn't see a dramatic change in field direction because the fields were roughly aligned. Both spacecraft are now in interstellar space, traveling outward at about 35,000 miles per hour for Voyager 1 and 34,000 miles per hour for Voyager 2. They're slowing down very gradually. The sun's gravity is still pulling on them, even at these vast distances. But the deceleration is tiny. They'll never slow to a stop. They'll never turn around and fall back toward the sun. They're moving fast enough to escape the solar system permanently. They'll keep going forever, unless they happen to encounter another star or get destroyed by a collision with something. In interstellar space, the Voyagers are still sending back data. They're measuring the density and temperature of the interstellar plasma. They're detecting cosmic rays and studying how they vary with time and direction. They're measuring the magnetic field strength and orientation. They're providing the first direct measurements of the local interstellar medium, the space in our immediate galactic neighborhood. One of the discoveries is that the heliopause is not smooth or stable. It's dynamic, changing shape and position over time. Voyager 2 detected a boundary layer just outside the heliopause, a region about a few astronomical units thick, where particles from the heliosphere are leaking out and mixing with interstellar particles. This boundary layer was unexpected. Theoretical models predicted a sharp transition inside the heliopause. Solar particles. Outside, interstellar particles. But the reality is messier. There's a zone where both populations coexist. Solar particles escaping outward. Interstellar particles penetrating inward. Magnetic fields from both regions tangled together. It's a dynamic, turbulent boundary rather than a clean dividing line. The magnetic field in interstellar space is stronger than expected, about 4 to 5 microgauss. A microgauss is a very weak field. Earth's magnetic field at the surface is about 500 milligauss, or 500,000 microgauss. So, the interstellar field is about 100,000 times weaker than Earth's field. But it's still stronger than models had predicted for this region of space. This stronger field affects how cosmic rays enter the heliosphere. It deflects and scatters them, changing their trajectories. The interstellar magnetic field acts as a filter, determining which cosmic rays can reach the inner solar system and which are deflected away. The plasma in interstellar space is denser and hotter than models predicted. The density is about 0.1 particles per cubic centimeter. That's about 40 times denser than the plasma in the heliosheath. The temperature is between 30,000 and 50,000 Kelvin, much hotter than the local interstellar medium was thought to be. Scientists think this high temperature is caused by compression. As the interstellar plasma hits the heliosphere, it gets compressed and heated, like air being compressed in a bicycle pump. The heliosphere is plowing through the interstellar medium, compressing the gas in front of it. This creates a shock wave in the interstellar medium, called the bow shock, though recent data suggests the Sun might be moving too slowly to create a true bow shock. It might just be creating a wave instead. Either way, the interaction between the heliosphere and the interstellar medium is heating and compressing the interstellar plasma. All of this is teaching us about the structure of the heliosphere and how it interacts with the galaxy around it. It's also teaching us about the local interstellar medium, the properties of the gas and magnetic field in our immediate neighborhood in the galaxy. Before Voyager, we could only observe the interstellar medium indirectly, by looking at how starlight is absorbed or scattered by interstellar gas, by measuring radio emissions from interstellar clouds, by studying the spectra of distant stars to see what elements are present in the intervening space. But Voyager is actually in the interstellar medium, sampling it directly, measuring its properties with instruments designed to study plasma and magnetic fields and energetic particles. It's the first time we've been able to do this. The first time we've sent a probe beyond our solar system and into the space between stars. And Voyager will continue this work for as long as its power holds out. The Voyagers are also carrying a message. Attached to each spacecraft is a golden record, a 12-inch gold-plated copper disc containing sounds and images from Earth. The record was the idea of a team led by Carl Sagan, the astronomer and science communicator who helped design the mission and served on the Voyager imaging team. Sagan assembled a small team to create the record's content. The team included Anne Druyan, a writer who would later become Sagan's wife, Timothy Ferris, a science writer and music producer, John Lomberg, an artist who had illustrated Sagan's books, and several others who contributed specific expertise. They had less than a year to complete the project. The decision to include a record on Voyager came relatively late in the mission planning. They had to design the record, choose its contents, produce it, and get it attached to the spacecraft before launch. All in a matter of months. The team approached the task with a mix of scientific rigor and artistic sensibility. What do you say to an alien civilization? How do you represent humanity in a message that might not be found for millions of years? What sounds and images capture the essence of Earth and its inhabitants? These were not easy questions. The team decided to include several types of content. Greetings in 55 different languages, from ancient Sumerian and Aramaic to modern Mandarin, Chinese, English, Spanish, and Hindi. Each greeting was brief, just a few seconds. Hello, from the people of Earth. We wish you peace and happiness. Simple messages of goodwill and friendship. The greetings represented the linguistic diversity of humanity. A reminder that Earth has many cultures, many ways of communication, many traditions. Not a single monolithic voice, but a chorus of different voices speaking different tongues. Natural sounds from Earth. Thunder, wind, rain, ocean, waves breaking on a shore. Volcanoes erupting, earthquakes rumbling, birds singing, frogs croaking, crickets chirping, whales calling, dogs barking, footsteps, heartbeats, laughter, a baby crying, the sound of fire, of tools being used, of horses' hooves, of a kiss. Sounds that would be familiar to anyone who lived on Earth, but completely alien to someone who had never visited our planet. These sounds paint a picture of a living world, a planet with weather, with oceans, with diverse life forms, a planet where beings walk on solid ground, where hearts beat, where children are born and cry. Music from different cultures and eras. Bach's Brandenburg Concerto, No. 2. Mozart's Magic Flute. Beethoven's Fifth Symphony. Stravinsky's Rite of Spring. Traditional music from Peru, Zaire, India, Japan, China, New Guinea. Blues, jazz, rock and roll. Johnny B. Good by Chuck Berry. Classical, traditional, modern. Western and non-Western. Music representing the breadth of human creativity across cultures and time. The team agonized over the musical selections. They wanted to represent humanity's musical heritage fairly. Not just Western classical music, though that was important, but also the musical traditions of Africa, Asia, South America, indigenous peoples. Music that showed humans have been making organized sound for pleasure and meaning for thousands of years. Music that communicates emotion even across language barriers. And 115 images encoded in analog form on the record. The images show the diversity of Earth and human civilization. Mathematical and scientific diagrams. The solar system with the planets labeled. The structure of DNA, the molecule that carries genetic information for Earth's life. Chemical formulas, atomic structure, anatomical diagrams of human beings showing skeleton, muscles, organs. Photos of landscapes from different climates. Deserts, forests, mountains, oceans, rivers, glaciers, showing that Earth has diverse environments. Images of life. Plants, trees, flowers, insects, fish, birds, mammals, microorganisms seen through microscopes. A vast range of life forms sharing one planet. Images of humans from different cultures, different ethnicities, different ages, different activities. People eating, people farming, people building, people reading, people running. Children playing, families together, individuals alone, showing human diversity and the range of human activities. Images of human technology and civilization. Architecture from different cultures. The Great Wall of China, the Taj Mahal, the Sydney Opera House. Modern cities with skyscrapers. Roads, bridges, vehicles. Factories, power plants, observatories. Showing what humans have built, how we've shaped our environment, the level of technology we've achieved. The cover of the record includes instructions on how to play it, drawn in symbolic form that's supposed to be understandable to any technological civilization. The instructions show how to mount the record on a turntable, how to place the stylus at the correct starting point, how fast to rotate the record. It indicates that the record should be played from the outside in, which is the opposite of how modern records are played. The images are encoded as video signals. The instructions show how to decode the signals and reconstruct the images. All of this using symbols and diagrams that don't depend on human language or culture. Universal mathematical relationships. Binary numbers. Physical constants like the hydrogen spin transition frequency. Things that any scientifically literate civilization should be able to understand. The cover also includes a diagram showing the position of the Sun relative to 14 pulsars. Pulsars are rotating neutron stars that emit regular pulses of radio waves. They're like cosmic lighthouses, flashing at precise intervals. Each pulsar has a unique pulse period. The diagram shows the direction to each pulsar from the Sun and the pulse period of each one encoded in binary notation. Because the pulses slow down at a known rate as the pulsars age, an alien civilization could measure the current pulse periods of these pulsars, compare them to the periods shown on the diagram, and calculate how long ago the record was made. How many years have passed since Voyager was launched? This gives the record a timestamp. It tells whoever finds it not just where it came from, but when. The diagram also serves as a map. If you know where these pulsars are and their pulse periods, you can triangulate the position of the Sun. You can figure out which star the record came from. It's a message that says we are here, at this location in the galaxy, and we existed at this time in cosmic history. The Golden Record is a time capsule, a message from humanity in 1977 to anyone who might find it in the distant future. The probability of an alien civilization encountering Voyager is vanishingly small. Space is incomprehensibly vast. The stars are separated by distances measured in light years. Light itself takes years to cross the space between neighboring stars. A spacecraft traveling at Voyager's speed would take tens of thousands of years to reach even the nearest star. And Voyager isn't headed toward the nearest star. The distance to the nearest star, Proxima Centauri, is about 4.25 light years, about 25 trillion miles. At Voyager 1's current speed of about 35,000 miles per hour, it would take about 75,000 years to travel that distance. That's assuming it was headed toward Proxima Centauri, which it's not. Voyager 1 is heading in a different direction entirely, toward the constellation Ophiuchus. In about 40,000 years, Voyager 1 will pass within about 1.5 light years of a star called Gliese, 445, in the constellation Camelopardalis. 1.5 light years is still an enormous distance, about 9 trillion miles. If that star has planets, Voyager will pass far outside any plausible planetary system. Voyager won't even be visible from those planets without a telescope. It will be a tiny, dark, cold object drifting silently through the void. After Gliese, 445, Voyager 1 won't come close to any other star for hundreds of thousands of years. It will spend the next millions of years drifting through the vast emptiness between stars. Voyager 2 is headed in a different direction, toward the constellation Sagittarius. In about 40,000 years, it will pass within about 1.7 light years of a star called Ross, 248. Again, a huge distance, far outside any planetary system. After that, Voyager 2 also drifts alone for hundreds of thousands of years before approaching another star. The chances that either Voyager will be found by an alien civilization are almost zero. The galaxy contains hundreds of billions of stars. The spaces between them are vast beyond comprehension. Voyager is a tiny object, smaller than a car, drifting through a volume of space measured in cubic light years. Even if a civilization is actively searching for artifacts from other worlds, the chances of them finding Voyager are infinitesimal. But here's the thing. The record will survive for billions of years in the vacuum of space. Long after Earth and the Sun are gone, Voyager will still be out there, drifting through the galaxy, carrying its message. The Sun will exhaust its hydrogen fuel in about 5 billion years. It will expand into a red giant, growing so large that it engulfs Mercury and Venus. Earth might be engulfed as well, or it might survive but be scorched lifeless. Either way, Earth as we know it will be destroyed. The Sun will then shed its outer layers, creating a planetary nebula, and the core will collapse into a white dwarf. A dense, slowly cooling ember about the size of Earth but with half the Sun's mass. And Voyager will still be out there, untouched by the death of the Sun, still carrying the golden record with its sounds and images from a world that no longer exists. In 1 trillion years, the galaxy will look very different. Star formation will have slowed as the gas available to form new stars is gradually used up. Many stars will have died. The Milky Way will have merged with Andromeda to form a larger galaxy. And Voyager will still be orbiting the galactic center, taking its quarter-billion-year journey around the merged galaxy. The record will still be intact. Gold doesn't corrode in vacuum. There's no oxygen, no water, no chemical reactions to degrade it. The record will look essentially the same as it did the day it was launched. A little pitted, perhaps, from micrometeorite impacts, but still playable, still readable, still carrying its message. It's conceivable, just barely conceivable, that billions of years from now, in a galaxy utterly transformed from the one we know, some civilization might find Voyager. They might be curious about this strange artifact. They might study it, decode the instructions, play the record. They might see the images, hear the sounds, read the greetings. They might learn that once, around a star long since dead, there was a planet where liquid water oceans covered the surface, where life evolved, where a species called humanity looked up at the stars and wondered if anyone else was out there. They might learn that we existed, that we thought, created, felt, loved, built civilizations, that we were here. It's a long shot, an incredibly long shot. But it's possible. And the fact that it's possible, that we've sent a message that could outlast our species and our planet and potentially be found by another intelligence, is itself significant. But the record wasn't really meant to be found. Not in any practical sense. Sagan and his team knew the odds. They knew Voyager would almost certainly drift through the galaxy forever without ever being detected. The record was meant for us. It's a statement about who we are, what we value, and what we hope to represent to the universe. It's a time capsule that says, this is Earth at this moment in time. These are the sounds of our world. This is the music we make. These are the languages we speak. This is what we look like, what we've built, what we've accomplished. It's humanity's way of reaching out to the cosmos, even knowing the reach will almost certainly go unanswered. Carl Sagan wrote about this in his book, Pale Blue Dot. He said, "The golden record is a testament to the human species, a declaration that we exist, that we're curious, that we care about knowledge and beauty and connection. Even if no one ever finds it, the act of creating it and sending it out into the cosmos has meaning. It represents hope. Hope that we're not alone in the universe. Hope that somewhere, somewhen, another mind might encounter our message and know that we existed. It represents curiosity. The fundamental human drive to explore, to reach beyond our boundaries, to ask questions about the universe, even when we might never hear the answers. It represents our desire to be remembered. To leave some mark on the universe that says we were here, we mattered. Our existence meant something. The Golden Record is one of the most poignant artifacts of human civilization. A message to the future, from a species that might not exist when the message is found. A greeting from Earth to whoever might be out there, sent knowing they'll probably never hear it. An act of faith and hope cast into the cosmic void. February 14th, 1990. Voyager 1 was beyond Neptune, heading into the outer solar system. Carl Sagan convinced the mission team to turn the spacecraft's cameras back toward the inner solar system one last time and photograph the planets. This maneuver was risky. Pointing the cameras close to the sun could damage them, and the spacecraft was so far away that Earth would appear as barely more than a single pixel. But they did it. Voyager 1 rotated and took 60 images, capturing 6 of the solar system's planets in what was called the family portrait. One of those images showed Earth. From 3.7 billion miles away, Earth appeared as a pale blue dot, a tiny speck suspended in a beam of scattered sunlight. 1 pixel. Less than 1 pixel. A fraction of a pixel, really. That's all Earth was, from Voyager's perspective. Sagan wrote about this image in his book, Pale Blue Dot. He wrote, "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. The image puts Earth in perspective. From that distance, from that vantage point, there are no national boundaries, no divisions, just a fragile blue world, alone in the vastness of space. Sagan saw this image as a call to humility and responsibility. We're small. We're vulnerable. We're the only home we've ever known. And we need to take care of it. After taking the family portrait, Voyager 1's cameras were turned off to conserve power. They've never been turned on again. The spacecraft now operates with a reduced set of instruments. Power from the RTGs is declining as the plutonium decays. Every few years, the mission team has to shut down another instrument to conserve power for the most critical systems. By the late 2020s, Voyager will no longer have enough power to operate any of its science instruments. At that point, the spacecraft will still be transmitting a carrier signal, a tone that confirms it's still alive, but it won't be sending data. Eventually, even that signal will fade as the last of the power runs out. The Deep Space Network will lose contact. Voyager will become silent. But the spacecraft will continue. It will keep moving through space at 35,000 miles per hour, coasting on the velocity it gained from those gravity assists decades ago. In the deep vacuum of interstellar space, there's almost nothing to slow it down. No air resistance. No friction. Just the faint pull of gravity from distant stars, too weak to make any noticeable difference over human timescales. Voyager 1 is currently the most distant human-made object from Earth. As of 2026, it's over 15 billion miles away. That's about 163 times the distance from Earth to the Sun. Light from the Sun takes 22.5 hours to reach Voyager 1. Communication with the spacecraft takes 45 hours round trip. Send a command. Wait 22.5 hours for it to arrive. Wait for the spacecraft to respond. Wait another 22.5 hours for the response to come back. Voyager 2 is slightly closer, about 13.5 billion miles away. Both spacecraft are leaving the solar system in different directions. They'll never encounter each other again. They'll drift apart, becoming more and more separated as they travel through the galaxy. So what did Voyager find? Over the course of nearly 50 years, what did we learn? We learned that the outer planets are far more dynamic and complex than anyone imagined. Jupiter isn't just a ball of gas. It has a complex atmosphere with storms that have raged for centuries. It has a powerful magnetic field that creates intense radiation belts. It has moons that are worlds unto themselves. Io with its volcanism, Europa with its subsurface ocean, Ganymede with its complex geology, Callisto with its ancient cratered surface. And it has rings. Saturn's rings aren't simple structures. They're made of thousands of narrow ringlets, shepherded by moons, shaped by resonances, constantly changing. Saturn has a hexagonal storm at its north pole, a feature so strange it defies easy explanation. Its moon, Titan, has an atmosphere denser than Earth's and a surface covered with lakes of liquid methane. Uranus and Neptune, the ice giants, have tilted magnetic fields, active atmospheres despite receiving almost no energy from the Sun, and ring systems of their own. Neptune's moon, Triton, has active geysers erupting from its frozen surface. We learned that planetary rings are common. All four gas giants have them. They're made of different materials: ice, rock, dust, and they form through different processes. Collisions between moons, material pulled from moons by tidal forces, remnants of objects that came too close to the planet and were torn apart. We learned that moons are not just dead rocks. They're geologically active, some of them. Io is the most volcanically active body in the solar system. Triton has geysers. Europa likely has a subsurface ocean that might harbor life. Enceladus, one of Saturn's moons, also has geysers. Though Voyager didn't discover them, the Cassini mission did later. But Voyager laid the groundwork by showing us that moons could be active. We learned about the solar wind and the heliosphere. We learned where the heliosphere ends and interstellar space begins. We measured the heliopause for the first time. We learned that the local interstellar medium is denser, hotter, and more magnetized than models predicted. We learned that cosmic rays are partially blocked by the heliosphere, which protects the inner solar system from some of the galaxy's radiation. We learned that the outer reaches of the solar system are shaped by the interaction between the Sun's influence and the interstellar medium. We learned that even after we thought we understood the solar system, there were still surprises. Every planet, every moon, every ring system had something unexpected. Nature is more creative, more complex, more interesting than our theories predicted. And we learned something about ourselves. We learned that humans can build machines that last far longer than anyone expected. Voyager was designed for 5 years. It's been operating for nearly 50. That's a testament to the engineers who built it, who thought through every possible failure mode, who designed redundancy and resilience into every system. We learned that we can explore places we can never visit in person. Voyager went to Jupiter, Saturn, Uranus, and Neptune. No human has been there. No human will go there anytime soon. But we sent our eyes and ears in the form of cameras and instruments, and they showed us those worlds. We learned that exploration is worthwhile, even when there's no immediate practical benefit. Voyager didn't bring back anything we could sell. It didn't find resources we could exploit. It didn't solve any problems we face on Earth. But it expanded our knowledge. It showed us the universe as it really is. And that knowledge has value in itself. Understanding where we are, what our place is in the cosmos, how the universe works, these are fundamental human desires. Voyager helped satisfy those desires. The mission cost about $860 million over its lifetime. That's less than the cost of a single modern aircraft carrier. For that price, we got detailed exploration of 4 planets, 48 moons, and the first direct measurements of interstellar space. It's hard to think of a better investment in knowledge. Voyager also inspired generations of scientists and engineers. People who were children when Voyager launched, who watched the images coming back from Jupiter and Saturn, who saw the pale blue dot photograph and felt a sense of wonder, went into careers in science and space exploration. The scientists and engineers working on current missions to the outer solar system, missions like Juno at Jupiter, Cassini at Saturn before it ended, New Horizons that flew past Pluto. Many of them cite Voyager as their inspiration. Voyager showed them what was possible. And Voyager changed how we think about life in the universe. Before Voyager, the search for extraterrestrial life focused on planets. Mars, Venus, maybe moons of Jupiter if they had atmospheres. But Voyager showed us that moons can be complex, geologically active, and potentially habitable. Europa's subsurface ocean might contain more water than all of Earth's oceans. If life can exist in Earth's deep oceans, near hydrothermal vents where sunlight never reaches, maybe it can exist in Europa's ocean too. Titan's thick atmosphere and surface lakes, though made of methane instead of water, might support a completely different kind of chemistry. Maybe life based on different solvents, different biochemistry. The discovery of active geology on moons expanded the possibilities for where life might exist. It's no longer just about planets in the habitable zone around stars. It's about moons, subsurface oceans, places where tidal heating provides energy even far from the sun. That's a direct result of what Voyager found. There's something poetic about Voyager's journey. 2 machines, built by humans, carrying a message from Earth, now drifting through interstellar space. They'll outlast us. Long after human civilization is gone, Voyager will still be out there. In 1 billion years, when the sun has expanded into a red giant and burned away Earth's atmosphere, Voyager will be far away, untouched, still carrying its golden record. In 5 billion years, when the sun dies and becomes a white dwarf, Voyager will still be traveling. It will orbit the center of the Milky Way galaxy, taking about 225 million years to complete one orbit, just as the sun does. But it won't be bound to the sun anymore. It's moving fast enough that it's on an independent trajectory. It's no longer a spacecraft. It's an artificial comet, an interstellar wanderer. Eventually, billions of years from now, Voyager might pass close to another star system. If that system has planets, and if one of those planets has a civilization, and if that civilization has the technology to detect and retrieve Voyager, they might find the golden record. They might decode it, see the images, hear the sounds, read the greetings. They might learn that once, around a star far away, there was a planet called Earth where beings called humans built this machine and sent it into the darkness. It's a long shot, an incredibly long shot. But it's possible. And the fact that it's possible, that we've sent a message that could outlast our species and potentially be found by another intelligence, is significant. It's a statement that we were here, that we existed, that we looked up at the stars and wondered, that we built tools to explore and learn, that we cared about knowledge and beauty and reaching out to the unknown. Voyager represents the best of what humanity can be: curiosity, ingenuity, persistence, the desire to explore not for conquest or profit, but for understanding, the willingness to invest resources in projects that won't pay off in our lifetimes, that might never pay off, but that expand the boundaries of what we know. The two Voyager spacecraft are among the greatest achievements of human civilization. They've traveled farther than anything we've ever built. They've shown us worlds we never imagined. They've crossed the boundary of our solar system and entered the space between the stars. And they're still out there, still sending back data, still exploring. 50 years after launch, Voyager is still teaching us about the universe. That's extraordinary. The next few years will be the end of Voyager's active mission. Power levels are dropping. Instruments are being shut down one by one to conserve energy. The plutonium in the RTGs is decaying, producing less heat, generating less electricity. By the early 2030s, there won't be enough power to run any instruments. Voyager will fall silent. But even in silence, it will continue. It will keep moving through the galaxy, a testament to human ambition and curiosity. A machine that exceeded every expectation. A traveler that will journey through the cosmos long after we're gone. When you think about Voyager, think about what it represents. Not just the scientific discoveries, though those are important, but the idea that we can reach beyond our world, that we can explore the unknown, that we can build something that lasts, that we can send a message to the future, to the universe, saying we were here, we wondered, we explored. Voyager is a reminder that humans are capable of remarkable things when we work together toward a common goal. The mission involved thousands of people, engineers who designed and built the spacecraft, scientists who planned the observations and analyzed the data, technicians who operated the Deep Space Network antennas, programmers who wrote the software, administrators who secured the funding and managed the project. All of them working together for decades to keep Voyager operating, to extract every bit of knowledge from its journey. And the mission continues. There are still people at NASA and JPL monitoring Voyager every day, tracking its position, receiving its signals, managing its power, making decisions about which instruments to keep running and which to shut down. They're shepherding these spacecraft through their final years of operation. When Voyager finally goes silent, when the last signal fades and the Deep Space Network can no longer hear it, it will be the end of an era. But it won't be the end of Voyager's legacy. The data it collected will be studied for generations. The images it took will continue to inspire. The story of its journey will be told and retold, because Voyager's story is fundamentally a human story. It's about our desire to explore, to learn, to understand our place in the universe. It's about our ability to build tools that extend our senses far beyond our bodies. It's about our willingness to invest in knowledge for its own sake. And it's about our hope that we're not alone, that somewhere out there, another intelligence might find our message and know that we existed. Voyager spent 50 years in space. And what it found was this: the universe is more beautiful, more complex, and more wondrous than we ever imagined. The outer solar system is not a cold, dead place. It's alive with activity, with moons that rival planets in their complexity, with ring systems of breathtaking structure, with magnetic fields and radiation and storms and volcanoes and geysers. The boundary of our solar system is not a sharp edge, but a dynamic shifting zone where the sun's influence gradually gives way to the interstellar medium. And beyond that boundary, in the vast spaces between stars, there is a universe waiting to be explored. We've taken the first step. Voyager crossed that boundary. It's in interstellar space now, the first human-made object to leave the solar system. It won't be the last. Other missions will follow. Other spacecraft will venture into the interstellar medium. Someday, perhaps, humans will follow too. But Voyager will always be the first, the pioneer. The machine that showed us it was possible. That's what Voyager found in 50 years of space travel. Not just data and images, though there are thousands of those. Not just discoveries about Jupiter's volcanoes and Saturn's rings and Neptune's winds, though those are all remarkable. What Voyager found was proof that we can do this, that we can explore the cosmos, that we can reach beyond our world and touch the unknown, that we can build machines that outlast us and carry our message to the stars. Voyager found the edge of our solar system, and then it crossed it. And in doing so, it showed us that the universe is open to us, that there are no boundaries except the ones we accept, that the cosmos is ours to explore, if we have the courage and the will to try. 2 spacecraft, launched in 1977, are still out there tonight, still traveling, still sending back signals from the edge of interstellar space, still carrying a golden record with greetings from Earth, still representing the best of what humanity can achieve. Voyager 1 and Voyager 2. 2 machines that changed how we see the universe. 2 travelers that will journey through the galaxy long after we're gone. 2 messages in bottles cast into the cosmic ocean. That's what 50 years in space found. And it's only the beginning. Thank you for joining me on this journey through the Voyager mission. If you found this exploration meaningful, a like or subscribe would help keep this channel going and reaching more people who share your curiosity about the cosmos. Voyager showed us that the universe is full of wonders waiting to be discovered. And every discovery raises new questions, opens new mysteries, invites us to explore further. The journey continues. The exploration never ends. And somewhere out there, beyond the edge of our solar system, 2 spacecraft are still traveling, still exploring, still representing us to the universe. Good night, and may you always look up at the stars and remember that we sent our ambassadors there.